The universe extended indisputably, expanding to immense lengths after its initial period. Following this rapid inflation, it continued to grow, though at a slower pace, eventually transforming into the universe we study today. This is known as the inflationary theory of the cosmic impact, the most widely accepted explanation for the universe's origin. However, some physicists argue that this theory does not accurately depict the universe's development. They propose that the universe existed before the Big Bang, stretching infinitely into the past and future. According to this view, the Big Bang was not an explosive event but a transition point where the contracting universe reversed direction and began expanding again. Their hypothesis suggests that the universe may continue this cycle of expansion and contraction indefinitely, challenging the traditional cosmological view that all matter originated from a singular Big Bang. Renowned physicist Brian Cox also questions the idea that something can arise from nothing, further complicating our understanding of the universe's origins. Recent findings by the James Webb Telescope have uncovered evidence that contradicts the notion of the Big Bang as the universe's beginning. These discoveries raise the question, if the Big Bang wasn't the start, what was? The idea that the universe had a beginning without a preceding moment dates back to Georges Lemaitre in 1927. Despite this, it is challenging to prove that the universe must have had a beginning. Much of cosmic history before the hot Big Bang has little to do with our current understanding of the universe. Some experts believe that the Big Bang does not mark the absolute beginning of everything. Instead, there is substantial evidence pointing to a non-singular start. The universe's inflationary period, which preceded the Big Bang, played a crucial role in shaping the cosmos. Initially, the universe was devoid of matter, photons, and anything else we recognize today. Space itself was filled with immense energy, which, over time, expanded rapidly and uniformly. This expansion slowed down, leading to the formation of the universe as we know it. This inflationary period is characterized by a superposition of instabilities across various scales, a defining feature of cosmological inflation. Living in an expanding universe means observing local regions where expansion has ended while surrounding areas continue to grow. Near the beginning of a major impact, regions close to you would disappear from view. This area, potentially no larger than a human-sized hamster ball, would undergo significant changes as energy transformed into matter and radiation. This process, called reheating, marked the end of inflation and the start of what we now call the Big Bang. As the universe continued to expand, regions where inflation ended would fill with antimatter and radiation, growing more slowly than still expanding areas. In an inflationary universe, distances between objects double at regular intervals. As time progresses, the expanding universe slows down, creating a disparity between regions where inflation has ended and those still growing. This dynamic means that different parts of the universe may never interact again. The area where we reside is fortunate to have ended its inflation phase, allowing energy to convert into a dense, nearly uniform expanse of particles. The quantum fluctuations that existed during inflation created the seeds for large structures in the universe. These density fluctuations, not visible in their initial state, eventually led to the formation of galaxies and other cosmic structures. The first observable evidence of these fluctuations comes from the cosmic microwave background, CMB, around 380,000 years after the Big Bang. Despite this, there are inconsistencies between the CMB and our current cosmological models, indicating that we might be missing key pieces of the puzzle. For instance, on large scales, the universe doesn't behave as expected. Light from the CMB is being lensed by matter between us and the CMB, bending and altering its path. The extent of this lensing does not always align with our predictions. The current model represents a significant milestone in cosmology, addressing key aspects of the cosmic microwave background, CMB, radiation. One striking observation is that the northern and southern hemispheres of the CMB sky exhibit distinct average temperatures, conflicting with the expectation of uniformity in the universe's early stages. This discrepancy suggests that the universe might not have started uniformly, leading to several anomalies. Another significant anomaly involves the Hubble constant, which measures the universe's expansion rate. This constant varies depending on whether it is measured from the CMB or from nearby stars, indicating that our understanding of the universe's expansion may be incomplete. These anomalies imply that we might be missing a crucial element in our interpretation of the universe. One proposed solution comes from loop quantum cosmology, LQC, an offshoot of loop quantum gravity, LQG. In LQC, gravity itself is made up of particles called quanta, forming the fabric of the universe. This theory posits a minimum size for space, known as the Planck scale, 1.0 times 10 to the power of negative 35 meters, which implies that the universe could never have reached a point of infinite density, as suggested by the traditional Big Bang model. Instead, LQC proposes that the universe underwent a big bounce, rather than a Big Bang, expanding again from a previously contracted state, similar to a phoenix rising from the ashes. This concept is not entirely new but provides a mathematical framework supporting the idea of cyclic time, akin to notions in Hindu cosmology. If LQC is correct, the early universe would have had a lower energy and density, potentially altering the appearance of the CMB as slight temperature variations across the sky. These variations, measured by the power spectrum, could offer substantial evidence of the universe's origins and support the possibility of a bounce. LQC thus presents a compelling alternative to the modern Big Bang theory, potentially resolving long-standing anomalies in cosmology and offering insights into the universe's beginnings. Moreover, it provides a plausible explanation for the discrepancy in average temperatures between the hemispheres of the CMB sky, addressing fundamental oddities observed in the CMB. Dr. Vinette Go of the National Institute of Advanced Studies suggests that these anomalies might not be mere measurement errors but could stem from quantum gravity effects early in the universe's history. The idea that the universe began with a vast leap is intriguing but requires further investigation. Cosmic inflation models support this view, suggesting that our observations might be limited to certain parts of the universe, complicating our understanding. Dr. Dwayne Johnson, a researcher and professor at Penn State University, highlights the challenge in validating such theories due to their large scale. However, integrating recent concepts like LQC and its implications holds promise in addressing novel cosmological issues. Despite these advancements, a significant question remains: did the universe have a beginning at all? Proponents of the universe having a beginning insist it did, raising questions about the nature of the event that started everything. Conversely, cyclic cosmology suggests an eternal universe, continually undergoing cosmic bounces. Physicist William Kenny of the University at Buffalo identifies a fundamental flaw in this idea: entropy. Entropy, or the measure of disorder in a system, increases with each cosmic bounce, implying a beginning similar to the Big Bang, contradicting the notion of an eternal universe. New cyclic models attempt to address this issue by incorporating vast stretches between bounces to dissipate entropy. Kenny's research suggests that the universe likely had a distinct beginning. Kenny's findings highlight the ongoing debate over cyclic universes, prompting further exploration into their viability. Proponents of cyclic universes have yet to fully address this critique. The scientific discourse around the topic continues to evolve, driven by the quest to determine the universe's origins and its ultimate fate. Quantum cosmology and cyclic models, which propose different mechanisms to account for anomalies, have garnered interest among cosmologists. Nelson dos Santos of the Brazilian National Institute for Space Research, who has explored bouncing and cyclic models, notes that while LQC bounces address CMB anomalies, they may not be definitive. He remains optimistic about the possibility of a cyclic universe, suggesting that an eternally existing universe seems more plausible than one created at a specific moment. While the universe's beginning remains a mystery, there has been intense discussion about its eventual fate. The universe's future depends on its composition, including dark energy and matter, determining its destiny. Essentially, there are two primary scenarios: endless expansion or contraction. In one scenario, the universe expands indefinitely, with stars eventually exhausting their fuel, leaving behind stellar remnants like white dwarfs and black holes. However, the universe's fate hinges on the nature of dark energy, a mysterious force driving its acceleration. If dark energy remains constant, the universe's expansion accelerates, leading to a cold, dark, big freeze, as matter disperses and entropy increases. Alternatively, if there is enough matter, the universe's expansion might slow and reverse into contraction, leading to the possibility of a cyclic model where the universe undergoes cycles of expansion and contraction without ever reaching infinite density or a specific beginning. Each cycle marks the start of a new era, providing a more comforting outlook compared to a cold, dark death. Regardless of the universe's fate, our presence at this particular moment is extraordinary. It highlights our unique role in the universe and the fundamental nature of knowledge in understanding the universe's vastness and inevitable reality. As we contemplate the universe's nature, we are compelled to consider the nature of our existence and the fleeting nature of time itself. Thank you for watching this episode. Your support drives us to deliver high-quality content, and we appreciate your comments on modern topics. Stay tuned for future episodes by subscribing and spreading the word. Until next time, keep exploring the mysteries of the universe.